wanted to go over number 24 because people said they were having some problems with it. So this value, the mass of your ice, which annoyingly is in kilograms, so keep your eyes peeled for that, is going to be different in different problems. I'm obviously going to do it with the 14.10 kilograms. The bottom line is you need to set the Q of the propane, C3H8, equal to the opposite of the Q of the water. I actually think it's easier to put the negative sign in front of the propane, but that's the premise of the problem. The next two steps you can do in an order different than what I'm going to do, but I'm going to figure out the Q of the propane first using some old school methods of finding heat of reaction from heat of formations. So I have written out the balanced equation for the combustion of the propane. That's something you should know, right? Plus oxygen yields CO2 plus H2O, and then you balance it. And then if you remember, the enthalpy of reaction is going to be equal to the sum of the heats of formation. You do products first and then subtract sum of heats of formation of the reactants. Okay, and then because this is specifically combustion, we can be a little more specific here and call it the enthalpy of combustion. So I sub my numbers in. Here are my products, and then here is my reactant. The oxygen doesn't have a heat of formation because it's already in its elemental state. So when I do that math, that equals negative 2,039. And the units there are kilojoules per mole. Now it's kilojoules per mole of reaction as written. Okay, so that's how you write your units. So what we have here is our Q for the propane. And if we want to take the opposite of the Q for the propane, we would just remove that negative sign. Next, we'll work on finding the Q of the water. So my biggest tip whenever you're using a heating or cooling curve is to just sketch out one, okay? So we're starting with really cold ice at negative 15 degrees Celsius, so that's going to be our start point, and then we're going to liquid water, so we know we'll be somewhere in this line at 80 degrees Celsius. So that's going to be before the boiling point of water. So that means that we have to heat up the ice to its freezing point. Then we need to melt the ice completely. And then we're going to need to heat up the resulting liquid water to 80 degrees Celsius. So here are the equations you're going to use. MC delta T for this first portion here, and we're going to use the specific heat capacity of the solid ice. Then for the melting portion is mass times heat of fusion. Notice I used mass here, so I'm going to have to use joules over grams for my heat of fusion units. And then MC delta T with the specific heat capacity of the liquid to get it to the 80 degrees Celsius. So I just sub my numbers in. The one thing of interest is right here. I use this from the heat of fusion in joules over grams from slides I had given out previously. Now I actually think it does, if you did the calculation on your own, go to 334.4 or something. So my answer is going to be a little bit off from what Chem 101 said. However, it still accepted my answer because it was within an acceptable range. So the answer that I got when I did this was 9.85 times 10 to the 6th joules. Now, I put that into kilojoules, so 9.85 times 10 to the 3rd kilojoules. Also, I think when I did the actual calculation, I kept the number out to more sig figs than this in my calculator. So just keep that in mind. Then for my final answer, I just did some dimensional analysis. So I said 9.85 times 10 to the 3rd kilojoules, which is the total amount of energy I need to convert my water. And then I used this equation right here and said, okay, there are 2,039 kilojoules of energy released for every 1 mole of the propane. And then I just went from moles of propane, C3H8, into grams of it, which is about 44 molar mass in the periodic table. And then that's going to give me my grams, my mass of the propane needed. So when I do that math, I got 212.6, although I probably should only be going to 3 sig figs, but I got 212.6 grams. I think the program had like 213.2, but you can see they allow for a little bit of wiggle room because there is kind of a lot of rounding that can go on. And like I use this value instead of the 6.02 kilojoules per mole. And then, I didn't do the conversion from there. So hopefully this helps you with number 24. That was, I think, the hardest problem on the Chem 101.